Hola, buenas tardes. Bienvenidos al Planetario de Madrid. Vamos a tener hoy un día muy especial porque tenemos una invitada muy especial y unos invitados muy especiales. Voy a hacer primeramente una pequeña introducción en español, también explicaros el por qué todo este acto va a ser en inglés. Supimos de la presencia de Jocelyn Bell, que es nuestra invitada, la doctora Jocelyn Bell, primera descubridora de los primeros púlsares, no del primero solo, sino de los primeros, junto con sus compañeros y sus maestros también. Y supimos de la presencia de Jocelyn Bell aquí en España y casi la pillamos como volando a través de nuestros compañeros de la Agencia Espacial Europea. Nos dijeron que estaba por aquí, mañana va a dar una charla allí. Ha estado por toda España haciendo un pequeño tour y aprovechamos la oportunidad pues, para hacerle aquí un pequeño homenaje, una pequeña, digamos, notar que su presencia es muy importante en el mundo de la astronomía. Es una de las personas más importantes desde el punto de vista de la evolución estelar y que han descubierto cosas que han confirmado muchísimas de las teorías. No os voy a hablar para nada de su currículum porque cualquiera de vosotros que entréis en Internet podréis ver la cantidad de cosas que ha hecho y sigue haciendo y seguirá haciendo. Esas están todavía por ver, pero es una persona muy señalada. Así que a partir de ahora vamos a hablar en inglés, si nos importa. Deciros a todos los que nos estéis siguiendo por el canal de YouTube que podéis activar la traducción, que tiene la herramienta y podéis seguirlo en español también. So, Dr. Bell, please come here. We will receive her with applause.
Thank you very much. Thank you. Thank you. Thank you very much.
It is a pleasure to have you here.
Thank you.
And you are very welcome to Madrid.
Thank you very much. It's very
our
good to
center.
be here, sir. Thank you for the invitation.
Okay. So, can you tell us something about your stage here in Spain? And first of all,
I have come from Almeria, and I was there for 2 days. I'm in Madrid 2 days. I go to A Coruña for 2 days, and then I go back to England.
and tomorrow you'll be in ESAC, in the European Space Center.
Yes, I
Okay.
will, indeed. Yeah,
Okay. We will speak about all your discoveries and all the whole stuff.
thank you.
And first of all, we want to introduce you the last show we have presented here in the planetarium, which is called Life's Question. It has been produced by a Colombian production company called Double Dome Films. I think you will like it. That will be in English.
James Bond.
The last question, which is not solved yet. Anyway,
Thank
welcome to all of us to the planetarium and enjoy the last question show. Felipe Orozco has been the director of the show. He's a Colombian guy, astronomer as well. Okay, thank you very much and enjoy the film.
Have you ever wondered about life? Perhaps you have wondered. How does everything around you connect? On this rare planet, there are millions of relationships between multiple individuals. The environments that these beings inhabit, or the food they consume, are of a diverse nature. We are without a doubt one of the most extraordinary phenomena in the universe. In your intestine, a very hostile place, colonies of bacteria survive thanks to the food you eat. And ironically, you depend on the same bacteria to digest your food. Whether inside your body or in lakes full of arsenic and salt, or in a small drop of water. Life has adapted and has made this planet an inhabitable world. This process, which began on our planet billions of years ago, has, with atoms, written a valuable legacy. An inheritance that is present in everything alive. An inheritance also present in you. By occupying the outskirts of our planet, we achieved a privileged perspective of the world we inhabit and the place we occupy in it. In this imbalanced system, we and millions of other species harness and transform the energy that emanates from the sun. But what are the possibilities of a complex process like this, also existing beyond heaven and beyond Earth? Maybe on another planet? Let's take a trip, but this time, let's travel through the questions. Those questions that the very existence of life make us ask. Welcome to Life's Question. We exist in a fertile time for life in the universe. Today, the ingredients necessary for life and for planets to be formed, like Earth, are found everywhere. But it wasn't always this way. At some point, the universe did not have enough ingredients to form something as complex as life. It didn't have oxygen atoms, like the ones you are breathing right now, or carbon atoms, like the ones that your body is made up of. Actually, for you to be here today, searching for new questions, certain stars had to be born, and others, unfortunately, had to die. Let's discover the origin of the ingredients that life is made up of. For this endeavor, we will travel back in time. Shortly after the birth of the universe, the first groups of atoms were formed: hydrogen and helium. Today, these atoms account for the majority of atoms in existence. They are also the raw material necessary to manufacture new elements. The main fuel which caused these gigantic stars to burn is hydrogen. Within the nucleus of these big furnaces, new atoms, such as oxygen or phosphorus, incubated. The smaller and later generation stars also used hydrogen and helium as fuel, which they also utilized to manufacture new types of atoms, such as carbon and nitrogen. What we call cosmic rays are really debris of atoms released at great speed by the violent death of certain stars. These small pieces of atoms collided with others in their path, creating new atoms such as lithium, beryllium, or boron. Recently, humans have also contributed to the alchemistic labor of the universe. we have synthesized new classes of atoms in laboratories, such as copernicium or Einsteinium. The bursts in which the biggest stars die are called supernovae. In a single explosion, the new material of the stars that has been fused from its nucleus is shot out at high speeds. Some heavy elements are formed from supernovae, such as the gold in jewelry or the iron in your blood. All of this cosmic activity, the violent bursts of material and energy, the life and death of small and giant stars, the cosmic rays, and the birth of the universe itself are the mechanisms that originate the ingredients from which life is made and have given form to the matter that exists today. Not all atoms have a leading role in this story. There are 6 elements that are the fingerprint of life on Earth: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, also known as chnops. These are the letters of the acronym with which the earthly work of life has been written. These elements, in turn, dance to the chemical evolution of the Earth and the solar system. They form the various chemical combinations which allow life to operate. We call them organic molecules. Organic molecules can form innumerable combinations when dissolved in water. From them emerged very complex chemical properties on Earth, including encoding and preserving vast amounts of information, the function present in DNA. Furthermore, time played a crucial role in the emergence of the affinity of these atoms, molecules, and later in life itself. At this very moment, millions of cells read and translate a message inside your body. This message has been encoded in our DNA and preserved by life. However, this genetic information has also been edited by viruses. These microscopic structures are a gray zone in our understanding of what is alive and what is not. Despite carrying pieces of DNA and their intriguing complexity, viruses are not classified as living beings. But this doesn't stop the hacking process that they do to living cells. What about other planets? Can life only exist on Earth? What is hidden in the unexplored landscapes of our neighboring worlds? Is the existence of life on Mars possible? This is the Mars Science Lab, also called Curiosity, an explorer responsible for finding answers and refining our questions about life's possibilities, while thriving in harsh environments like those on Mars. Its mission, which is just beginning, is to gather enough information about the red planet's surface and send it back to Earth. The gases in Mars' atmosphere, the chemical composition of its soil, and the amount of water on its surface are data elements that will help us understand the mysterious past of this planet. Half a ton of chassis, scientific instruments, atomic batteries, and lasers for examining rocks could provide us with a better understanding of this nearby world, which once had oceans and rivers flowing across its surface. Did Did something similar to life ever exist on Mars? Could it exist today? Curiosity has studied some rock samples, and despite not finding life, it has detected in some of them high levels of methane gas, levels almost 21 times higher than previous readings. Methane is an organic molecule made of carbon and hydrogen. Here on Earth, it is food for certain types of organisms, but it is also the residue that other organisms release. Current characteristics of Mars, including seasons, a similar day duration to Earth's, organic molecules, and frozen water, provide an advantageous environment for future life habitability, and it depends highly on our perseverance to continuously discover this world. Life and space rocks are closely related. Even before Earth was formed, some rocks carried within them an essential ingredient for life: massive amounts of water. In fact, much of the water that is currently on the surface of our planet came to us thanks to comets. These mountains of ice and rock, which drift through the solar system once every few decades or even hundreds of years, contain frozen water, precious metals, and again, organic molecules. Despite not being a life-friendly environment, comets are vehicles that carry much of the water available in our solar system. Alongside the gaseous planets, an unexpected possibility for life is available. Their moons. These little worlds that orbit the giant planets can hide seductive scenarios for life. Enceladus is a moon of Saturn from which water vapor spouts. This tiny world, just 500 kilometers in diameter, offers us great questions. Liquid water spouting from a moon? That far from the sun? These geysers expel salt water from an inner ocean, which gestates in the belly of this moon, thanks to the heat emanating from its nucleus. This proves that the environments necessary for life, like oceans, are possible beyond Earth. Beyond Enceladus, in the interior ocean of Europa, one of Jupiter's moons, is an amount of water greater than all that exists on Earth's surface. In this type of lunar oceans, there could be conditions similar to those present on Earth before life was formed: oceanic environments, heat sources, and organic molecules. Moons like Enceladus or Europa are worlds that challenge our certainties about the environments possible in the solar system. There is enough energy inside them to melt ice into water, making ocean environments possible. Titan is the largest moon around Saturn. It is even larger than the planet Mercury. This toxic world has conditions hazardous for life as we know it, such as liquid methane rains and lakes. However, it has an important attribute: a dense atmosphere. These conditions reveal a highly diverse solar system where water is abundant and ocean environments or atmospheres are not exclusive conditions of the planets. There are still 200 worlds to discover in the solar system. What about the other planetary systems? The Sun is a small star, just a point of light, which together with hundreds of billions of other stars make up our galaxy. There are millions of planets and moons out there. Some of them should contain environments favorable for life. The super-Earths are rocky worlds almost twice the size of our planet. These rocky planets could contain much more water than Earth, and most likely have abundant chnops, atoms. Also, the moons outside our solar system, or exomoons, could provide a wonderful chance for life. We know about the immeasurable amount of stars in the universe. Now imagine for a moment the number of planets around them. Moreover, imagine the number of moons that exist in the entire universe. Our limited observation has allowed us to contemplate diverse possibilities for the development of a complex process such as life. But this process could also exist in the future of new worlds that are now being born. This galaxy, called the Milky Way, is just a small island inside a universe that has hundreds of billions of them. The matter from which the moons, planets, stars, and nebulae are made is only 5% of everything in existence. The rest of the cosmos, 95%, seems to be made of dark matter and energy, two entities that we are just now discovering. We are part of one of the most exotic forms of matter that exists, atoms. The evolution of the universe and the passing of time allowed life to emerge on a planet like Earth. In all this vastness, we embody that small but inevitable possibility. Also the evidence of an intelligent life that is able to ask questions about itself, and consequently help our cosmos become aware of itself and its plural reality, a multiverse. Astrobiology is the study of the phenomenon of life as a spontaneous property of the universe. Two prominent scientists in this area, Carl Sagan and Frank Drake, designed a radio signal message to test the power of a radio telescope. This 210-byte message travels at the speed of light to a star cluster and carries with it information about Earth, life on it, and the solar system. It is a message in a bottle in the oceanic reality of the universe that may or may not have a recipient. We have explored the origin of the ingredients that are indispensable for life on Earth. Conditions inside and beyond the solar system are ruled by the same physical laws. It's impossible to not guess another possibility for a phenomenon such as life. The lunar oceans and super-habitable planets can house conditions suitable for chemical evolution. This fertile quality of the universe has evolved thanks to mechanisms such as the life and death of stars. This part of the universe that we call life, capable of adapting and being resilient to extinction on Earth, is the same that drives us to search for answers about our origins. oceanic environments where Earth's organic matter could evolve appear to not be so scarce in the universe. We are the aware part of the universe. You are the part of the universe that can study itself, and then wonder about the close connection between everything in cosmic evolution. You are the part of the universe that is able to formulate life's question.
That was the show. Thank you. Okay, now the next part of the entire show is a video we have prepared about the discovery of the pulsars. It has been narrated by Cristina Garay, who is one of our astrophysicists, and it has subtitles in English for you, Jocelyn. And it is about 5-6 minutes. Okay, so let's start with it.
Una noche de 1899, mientras trabajaba en su laboratorio, el ingeniero inventor serbocroata Nikola Tesla detectó unas débiles señales en su receptor de radio procedentes del espacio, que sugerían un código numérico implícito. 1, 2, 3. Eran tiempos en los que Percival Lowell creía ver en la superficie de Marte toda una red de canales de origen artificial, mientras que la novela La Guerra de los Mundos, de Herbert George Wells, se popularizaba rápidamente. Así que no es extraño que Tesla creyera que procedían de Marte y que todo aquello podía ser la prueba inequívoca de la existencia de una inteligencia alienígena. ¿Había alguien ahí fuera intentando contactar con nosotros? La existencia de emisiones radio de origen extraterrestre se confirmó poco después, pero resultaron ser completamente naturales. El Sol y los planetas eran un ejemplo de ello. Unos 30 años más tarde, en 1932, Carl Jansky detectó emisión radio de procedencia mucho más lejana, del centro de nuestra Vía Láctea. Daba así comienzo una nueva forma de estudiar el cosmos, la radioastronomía. Grandes radiotelescopios empezaron a construirse por todas partes, con el fin de escuchar lo que el universo tenía que decirnos. En 1967, el astrónomo británico Anthony Hewitt inició una serie de observaciones que condujeron a un descubrimiento inesperado. Su joven estudiante de posgrado, Jocelyn Bell, detectó algo extraño entre los datos de su radiotelescopio. Una señal de radio de muy corta duración, emitida desde la constelación de Vulpecula y que se repetía exactamente cada 1,33 segundos. Parecía demasiado rápida para provenir de un objeto celeste, por lo que Bell y Hewitt denominaron de forma burlona la nueva fuente LGM1, por las iniciales en inglés de Little Green Men, hombrecillos verdes. Y aunque siempre pensaron que tenía origen natural, cabía la posibilidad real de que se tratara de una señal de una civilización extraterrestre. No, estaba claro que se trataba de un nuevo tipo de fuente natural. En 1968 publicaron el descubrimiento y al poco rebautizaron a este nuevo tipo de objeto como Pulsar, acrónimo de estrella pulsante en inglés, una estrella que, por algún motivo, emitía pulsos de radioondas. La noticia causó gran revuelo y al profesor Hewitt le fue otorgado el premio Nobel en 1974 por el descubrimiento de los púlsares. De forma totalmente injusta, Jocelyn Bell no compartió el prestigioso premio con su profesor. Un púlsar es una estrella de neutrones. Es algo parecido a un faro, cuya emisión solo vemos cuando su haz giratorio apunta hacia nosotros. Un objeto extraordinariamente compacto que rota sobre sí mismo a velocidad de vértigo, lo que produce campos magnéticos increíblemente intensos. Estos hacen que la radiación se emita en una dirección bien definida, dada por su polo magnético, que generalmente no coincide con su eje de rotación. Cada vez que el haz apunta a la Tierra, recibimos un pulso. Las estrellas de neutrones son el cadáver de estrellas masivas, de masas entre 8 y 10 veces la masa del Sol. Dentro de estas estrellas, cuando el núcleo agota su combustible, se contrae y colapsa, mientras que sus capas externas se lanzan al exterior violentamente en una explosión gigantesca que denominamos supernova. Ese núcleo estelar hiperconcentrado en una esfera de pocos kilómetros es una estrella de neutrones, y se llama así porque está compuesta esencialmente por estas partículas. Una masa de hasta 2 veces la masa del Sol contenida en un objeto de apenas 10 o 20 kilómetros de radio. El tamaño de una ciudad como Madrid. Algo tan denso que equivale a concentrar toda la masa del monte Everest en una pequeña canica. Durante la formación del objeto se conserva el momento angular de la estrella inicial, por lo que al haber disminuido tan drásticamente de tamaño, acaba rotando a velocidades de vértigo. Esta rotación es el motivo de que los púlsares emitan ráfagas de ondas radio a intervalos extremadamente regulares. Hoy día se conocen más de 700 púlsares, con períodos de rotación que van desde el milisegundo hasta pocos segundos. El más famoso se encuentra en el interior de la nebulosa del Cangrejo, con un periodo de 0,033 segundos. Es decir, gira 33 veces en cada segundo. En el mismo lugar del cielo, astrónomos chinos y árabes registraron una supernova en el año 1054, lo que nos permite establecer esa correlación entre supernova y estrella de neutrones púlsar, siendo la nebulosa del Cangrejo el resto de aquella explosión observada. La extrema regularidad de los púlsares los convierte en referencias únicas, cuya observación podría permitir la navegación a través del espacio profundo. Un auténtico sistema de posicionamiento global o GPS interestelar. Si una nave espacial pudiera recibir las señales de un cierto número de púlsares cuya posición es conocida, sería relativamente sencillo determinar su localización. Igual que hace la tripulación de un barco en el mar con los faros costeros, solo que en el espacio. Esta técnica ya se ha probado con éxito. En el verano de 2017 llegó a la Estación Espacial Internacional el instrumento NICER, del inglés explorador de la composición interior de las estrellas de neutrones. Después de pasar día y medio observando una serie de púlsares, el aparato determinó su propia localización en el espacio con un margen de error de solo 5 kilómetros. En cuanto a los hombrecillos verdes, aún no han sido encontrados, pero quién sabe, seguiremos buscando.
Okay. Let me introduce you Mark Kidger. Dr. Mark Kidger is one of the astronomers of the ESAC, European Space Astronomy Center, who is going to give us a talk about what is think to be Betelgeuse. Actually,
Yes.
no? Is it the future will be more or less, we think, or you think, or astronomers think, that will be a pulsar. So let's start with your talk. Thank you very much for coming.
Okay.
It's a pleasure to be here too. And later on, Dr. Bell and Dr. Kidger will answer your questions. Not only your questions, but the online questions, if possible. Okay, thank you very much, Mark.
Okay.
And good to see you.
Muchas gracias. Do you speak English? Oh, somebody's still awake. Wonderful. Now, I've been told to keep still. This is very difficult for me. I can see Tilma watching me. Anyway, it's often said that we are just stardust. But most people don't realize that that really is absolutely, quite literally true. And going back a year and a half, winter 2019-2020, something extraordinary happened in the constellation of Orion that has a relationship with the fact that we are here and that we are stardust. Betelgeuse, it's up there in the circle, the shoulder of Orion. It's normally about the 10th brightest star in the sky. I say normally because it's a variable star. It varies in brightness, usually only modestly, but it varies. So sometimes it's brighter, sometimes it's fainter. But what happened in November 2019 was something very unusual in this star. It started to fade, and it continued and continued to fade. Here we've got a before and after picture. Left before it started to fade, right as it was fading. It really did change the constellation of Orion. By February 2020, before our lives had all been changed completely by COVID and all our patterns of behavior had changed, Betelgeuse had faded to only about a third of its normal brightness. And the difference that that made to the constellation, if I flick backwards and forwards, really enormous difference. Most people had other things to worry about at the time. But for astronomers, this really was a quite extraordinary event. And people started to wonder, how much fainter is Betelgeuse going to get? Is it just going to fade away completely? Some people had even more exotic ideas. Was the star in crisis? Was it about to explode? People have a lot of imagination sometimes. In fact, even the New York Times picked up on the story, and it had a headline, Betelgeuse, just a fainting spell, or is Betelgeuse about to blow? And the story went on to explain that astronomers thought that maybe Betelgeuse was about to explode as a supernova. On what evidence they said that, and what astronomers they'd spoken to, I have no idea. But it's the New York Times, so it must be true. However, Betelgeuse didn't fade away, didn't disappear, and everything came back to normal. By the end of April last year, Betelgeuse was back to its normal brightness. In fact, even a little bit brighter than normal. Certainly when I was watching it before it disappeared into the sunset last year, it was actually a bit brighter than it would normally be. So the question people asked, what on Earth or what in space happened to Betelgeuse? Was it the beginning of the end for the star? There you've got a comparison, two images, the star before and after. Actually, to me, that's not very impressive. It doesn't look so different. But really, it was only about a third bright. In fact, what we know now is that Betelgeuse's light was dimmed by an enormous cloud of dust that it belched out into space in front of the star. And that cloud of dust, before it dispersed, dimmed the light of the star. We were seeing the star through a thick fog of dust. And when the cloud dispersed, Betelgeuse returned absolutely to normal. So anyway, let's go back, let's meet Betelgeuse. Now, a contestant, for example, in some interstellar quiz game. So how would he present itself to the presenter of the program? Well, it's in the constellation of Orion. It's also known as Alpha Orionis. It's got that nickname, the brightest star in Orion, which it isn't. In fact, rarely is. You don't normally ask someone their age, but we can reveal Betelgeuse is about 10 million years old. You know, it's a real youngster as stars go. And it occupies its time as a red supergiant star. It's a big star. The embarrassing thing is we don't actually know how far away Betelgeuse is. It's somewhere probably about 500, 700 light years away, but we really don't know. It's far enough away that we can't actually measure it exactly. Moderately variable, normally the 10th brightest star in the sky. Not a curriculum quite as brilliant as Jocelyn's, but it's not bad as stars go. You know, it's a decent one. But it's a very special star. It's a special star in many ways. Why are we so interested in this star, Betelgeuse in Orion? Well, not only is it extremely large, but it's also relatively nearby. To an astronomer, 500 light years, that's not worth worrying about. You know, it's on your doorstep. You don't worry about such tiny distances. It may actually be the nearest star that can become a supernova. However, the other photograph there, that's the constellation of the Scorpion, Antares. The bright red star in the Scorpion might dispute that title with Betelgeuse because it's about the same distance, it's about the same size. Nobody can quite decide. However, Betelgeuse, however big it is, we know it is exceptionally big. It is very, very large indeed. Historically, people have estimated the mass could be anything between 6 and 30 solar masses. So between 6 and 30 times the mass of our sun. The best guess is that it's somewhere in the range between 10 and 20 solar masses. So 10, 20 times the mass of the sun. It's also big in another sense. Apart from the sun, which is cheating because it's so close, there's only one other star in the sky that is as large in apparent diameter as Betelgeuse, and that's R Doradus, a star in the constellation of Doradus, El Pez Dorado, in the southern hemisphere. We can't see it from Madrid. You have to go down south of the equator to see it properly. In fact, special instruments, special techniques can even reveal the disk of Betelgeuse. There we've got a photograph. In fact, we've got two photographs of Betelgeuse. One with the Hubble Space Telescope and another using a technique called speckle interferometry. And those structures on the disk of the star, they are quite genuine. The star is not an even disk of brightness. How massive is Betelgeuse? Well, it's very difficult to say. There are many, many different estimates that have been published. Part of the problem is that we don't know how far away Betelgeuse is. There are lots of different estimates of the distance. They range from about 350 to 850 light years away. In fact, the more recent the estimate, the more distant it is. But none of the estimates actually agree with each other very well. If you take the range of distances that are estimated, people would say measured, but I'd say estimated because the errors are so big. It turns out to be a factor of 10 in luminosity, the real brightness of the star. So it's not unsurprising that it's a bit difficult to work out exactly how massive Betelgeuse is. There are various recent projects that have tried to work out the mass of Betelgeuse using very sophisticated techniques. And they've come up with completely discrepant results. That's the marvel of astronomy. When the data you've got is perfect, you can get perfect precision. But rarely is our data perfect. And so 3 very recent, supposedly extremely reliable determinations have come up with values from about 7.7, so about 8 times the mass of the sun, up to 23 times the mass of the sun. That's a pretty big range of uncertainty. Some estimates say that Betelgeuse is a lot bigger and more massive than Antares. Others say that Antares is bigger and more massive. So, a star this big, a star as big as Betelgeuse, Antares, will probably go out with a bang. Whichever way, whether Antares is the bigger, Betelgeuse is the bigger, one thing we know for certain is that if Betelgeuse is more than 10.4 times the mass of the Sun, it will explode as a supernova. If it's less than that, things are a bit more complicated. You do get a supernova, but not a decent, honest-to-God, really big bang. You get a much smaller bang. What everybody would like is to get a really big bang from Betelgeuse, for reasons I'll explain a little bit further on. But for this to happen, Betelgeuse has to turn into what we would call an 8-layer onion. You know what an onion's like. You cut it open, it's skin after skin after skin inside. And that is what we need Betelgeuse to be if it's going to turn into a supernova. It's got to be an 8-layer onion. Now, what does that mean? Now, in our Sun, as we saw in the video before, hydrogen is converted into helium. That produces an enormous amount of energy, heat, and the heat pushes the star out and keeps it inflated. The gravity wants to crush the Sun down. The fact that it's hot in the center keeps it expanded like a balloon. So when the hydrogen runs out in the center of the Sun will die, and so will the Earth. However, don't worry. Don't cancel your insurance policy. We've got 5,000 million years to go. Still time to see a couple more films or football matches, whatever you prefer to do, to relax in the evenings. However, in a star like Betelgeuse, if it's bigger than 10.4 solar masses, what happens is when the hydrogen runs out, the star collapses, or at least the center of the star collapses, it gets hotter and hotter inside, and then suddenly helium starts to combine to form carbon. So instead of having 4 hydrogen atoms producing helium atom in the center of the star, you get 3 helium atoms producing a carbon atom. For a while, the star will continue to burn, and then the helium runs out. What happens then? The star collapses again, it gets hotter and hotter in the center, and then carbon starts to burn to form neon gas, as in your neon lights. And we have a cycle that repeats. The star collapses, it heats, collapses, heats again, and you have one element after another starts burning. And as you go out from the center of the star, in the very center where it's hottest, you're burning the heaviest elements. And then in a series of shells outside, where it's not so hot, where it's a bit cooler, only a few tens of millions of degrees centigrade, positively cold, you're still converting what remains of the hydrogen into helium. So you have a series of shells around the center of the star, like a giant onion. And then finally, we get to the point where if the center of Betelgeuse can reach 2,700 million degrees centigrade, you form your 8th and final layer. Silicon will start to turn into iron. And then we get to a crisis, because iron will not burn. There are no nuclear reactions with iron that produce energy. They all consume energy. What will happen? Suddenly, the heat in the center of Betelgeuse that is keeping the star inflated holding it up against the force of gravity is going to switch off. Betelgeuse will have a fatal heart attack. People don't realize overweight in stars, obesity in stars also causes fatal heart problems. What will happen? The star will collapse. As it collapses, all the mass of the star will be forced into a small volume in the center, and we will have an immense orgy of nuclear reactions. And 90% of the mass of the star will be blasted into space. The other 10% is what our special guest is interested in. But 90% of the star will be blasted into space. When that happens, that's a supernova explosion. For a few days, a few weeks, a few months even, that star, the supernova explosion, can become as bright as a whole galaxy of 100,000 million stars. Not always, but the one at the top, you can see the supernova between the lines. It's brighter than the whole galaxy. The one underneath wasn't quite so bright. The explosion launches all the elements that were formed inside the star out into space at tremendous velocity in an expanding cloud. What do we get? We seed space with carbon, iron, calcium, phosphorus, nitrogen, all the elements that make up our bodies and allow us to live and breathe, as we saw in the video. Carbon, which is the basis of all organic matter. Nitrogen, which is essential in proteins. Oxygen, we breathe. Iron in our blood. Calcium and phosphorus make up our bones and teeth. All these elements formed in the center of dying giant stars like Betelgeuse and were shot into space in supernova explosions. And it turns out that the only reason why life is possible, why our planet Earth exists even, is because of the noble sacrifice of stars like Betelgeuse that died and seeded space with these elements. Now, this supernova hasn't yet happened. Possibly it will never happen. But, as we saw in the video, there was a supernova in our galaxy in the year 1054, almost exactly 1,000 years ago now. And it was recorded by the Chinese. This is a Chinese chronicle. The parts in yellow, I won't bother to translate. I assume everybody here speaks perfect Chinese. Chronicle the Chinese observations of what they called a guest star, a brilliant supernova. It was 6,000 light years away, but it was so brilliant that it was visible in broad daylight for several weeks. And even, this is the one case, we believe, where Native Americans observed a supernova, an astronomical phenomenon. There's a picture of a pictograph of the crescent moon and a star by it. And that configuration actually would have happened shortly after the supernova appeared. So we believe that this is a Native American representation of a supernova. Why would this be interesting? Well, if Betelgeuse were to become a supernova, it would probably become as bright as a half moon. Night time would be abolished, possibly for several months. There are even optimists who suggest that Betelgeuse would become as bright as the full moon. So astronomy at night would become almost impossible for some time, possibly for several months. quite annoying to astronomers, but quite fascinating as well. Is Betelgeuse, though, about to become a supernova? The answer is that the New York Times may just have used a little journalistic exaggeration. It's very unlikely. Some people seem to doubt the New York Times. Well, why is it very unlikely? The answer is that the end of a star like Betelgeuse will be extremely rapid. When the course of Betelgeuse switches off, the collapse and the explosion will only take about 2 seconds. And the first news that we would receive that Betelgeuse has blown up would be that neutrino detectors on Earth would be swamped by 1 to 2 million neutrinos. Now, when the supernova in the Large Magellanic Cloud in 1987 exploded, that produced 23 neutrinos that were detected on Earth. We're talking about a signal 100,000 times stronger. That would be quite something. Turns out that by the time a star like Betelgeuse starts to burn its carbon, the end comes very fast indeed. The carbon in Betelgeuse will only last for about 1,000 years. The oxygen, after it's burnt the carbon and starts burning oxygen, will last less than a year. Silicon, the very last stage, the very last skin of the onion, about 2 days. So, if Betelgeuse is already burning oxygen, for example, it's about to blow up at any moment. If it's burning silicon, be prepared for a blinding flash when you go out of the planetarium tonight. Not very likely. In fact, we believe that, in fact, Betelgeuse is about 80 to 90% through its supply of hydrogen. It's towards the end of burning helium, but not yet burning carbon. So the best guess is about 100,000 years till it explodes. However, hope springs eternal, and there are a lot of people who would love to be wrong about this. And to go out one night and suddenly discover that there is a star as bright as the full moon in Orion. What would be left after supernova Betelgeuse, apart from a great expanding cloud of dust and gas seeding space? Well, we've seen these images, I think, before. 1967, young graduate student at Cambridge University was examining the scintillation, the twinkling of radio sources caused by clouds of plasma in the solar system. She had 5 kilometers of paper charts like this to examine. And she noticed that about the same time, not even every night, most nights, a little signal that she called scruff appeared in the chart, something that shouldn't be there. Now, for me, the fact that somebody was capable of looking at 5 kilometers of paper charts and noticed this little tiny signal that only lasted for a few seconds each night and recognize that it was something unusual, that is really dedication. That's quite special. It was in the constellation of Vulpecula. The first pulsar, the pulses, were identified on November 28th, 1967. And then on December 21st, not content with one, Jocelyn found another one. And now we know, in fact, over 2,000 pulsars. That's a quite remarkable number. 2,000 remnants of dead stars. Oops, pressed the wrong button. So, what is left after the explosion of the supernova? This tiny neutron star flashing like a lighthouse. And there below you can see the crab pulsar. And you can see how it flashes on and off as the pulsar spins round and round and round. Now I know Jocelyn has a very interesting anecdote about this star. I have read the wiki page. So see if we can persuade her to tell us about this anecdote afterwards. Very curious observation. That's about twice the mass of the sun packed into a diameter of just a couple of tens of kilometers. And as in the crab pulsar, just very occasionally, there's only one or is it two known where you can actually detect it visually. You can see the star winking through a telescope. Maybe one day Betelgeuse will become a pulsar too. But put a note in your diary, you're going to have to be patient around about 100,000 years. But patience is a virtue. Thank you for watching.
Thank you, Mark. Now, Dr. Bell and Mark will answer your questions, if so. And thank you very much. It was very, very fun.
Thank you.
And
Placer.
Dr. Bell, please. Are you ready to answer whatever
Yes.
question, except for the existence of God?
Thank you. Thank you very much. Thank you.
Os vamos a pasar el micrófono si queréis. No lo acerquéis mucho por los temas que ya conocéis, pero bueno, levantáis la mano y os acercan el micrófono.
Although with these lights, it's actually rather difficult to see anybody there.
While we're waiting, can I tell you about 1957? 10 years before I discovered pulsars. We are in Texas, in the United States. We are at McDonald Observatory. And one night every month, there is public viewing. People can come and look through the telescope. The telescope is set on that curious star near the center of the Crab Nebula. And members of the public come and say, "Oh, amazing, fantastic," whatever they said in 1957.
Probably gee whiz.
Maybe gee whiz, yeah. Gee, we're in the States. And a young woman steps up to the telescope and says, "That star's flashing." And the night assistant starts to explain that stars can change their brightness because of the Earth's atmosphere. She says, "No, I know about that. My job is to fly aeroplanes from the factory where they were built to the customer. I fly at night. I know about that scintillation. This star's flashing." There was a young man who was a student working there for the summer, and he recorded this, made a note of this. Nobody else took any notice, and the next member of the public stepped up to the thing and said, "Oh, gee." And so it went on. Now, that pulsar flashes 30 times per second, 30 hertz. And we now know that it flashes in light, in the optical, as well as the radio. Not many people can see flashing that quick. But in Canada, the lights, the electric power, used to be at 30 hertz, 30 times per second. And some people, especially young women, could see the flashing. And it was very annoying. So we know that some young women can see 30 hertz. And the student who was there for the summer, now an old man, believes that she saw the Crab pulsar flashing in the optical. But nobody took any notice. And it was another 10 or maybe even 12 years before the Crab pulsar was rediscovered. So, listen to the young women.
Yeah, how physics would have changed if that observation had been taken seriously.
Yeah, it would have changed, and we would have looked for other optical pulsars, and there aren't any. So maybe it wouldn't change. This funny star, Minkowski star, was funny because it flashed. Ha ha. End of story.
Si la gente prefiere en español, se puede también. Hay un valiente inmediatamente. Sí.
Okay. What was your psychological state before your discovery, during it, and after it, if you remember?
I came to Cambridge to do my PhD from the north and west of the British Isles, the mountainous, heathen, uncivilized part of Britain, as Cambridge thought. And I come to Cambridge and everybody is terribly suave and extremely clever. And they know it. And they have a right to be there. And here's me, the heathen. They're all very bright here. I'm not that bright. They've made a mistake. I shouldn't be here. I'm not clever enough. But I am here. So they will discover, they will throw me out. But until then, I will work my very, very hardest so that when they throw me out, I will know I have done my best. And I just was not clever enough for Cambridge. So I'm being very, very thorough. And that's how I notice this about 1 part in a million anomaly that was the first pulsar. Following the discovery, life became very busy because we had to try and understand what these things were, as well as I had to keep my thesis project going. So it was hard work, but it was a very special time. So thank you for the question.
So what you're saying is it was about that much, 5 millimeters
Yes.
in 5 kilometers.
Yes. No. Have we done the sums right? Yes, you have done the sums right.
Yes.
Yes. No, okay, it's not that
That's
remarkable.
patience.
Yeah, I think I've done the sum slightly wrong, but it's not quite that bad. But it was a very small anomaly.
First of all, sorry for my pronunciation. What do you feel when you look at the stars at night, knowing that you discover some pieces of our universe?
That hadn't crossed my mind. I mean, they were there before. They are still there. I have not changed the universe. The universe is the universe. And I find it fascinating. And I hope you do too, because you've had a wonderful explanation of some of the important bits of the universe. Studying it is for a job. You get money for studying the stars. Wow.
Hello, my name is Isabel. First of all, thank you for being here with us here in Spain. I would like to know if you have any intuition about something it has not yet proved, or something you would like that could be true, proved during our lifestyle now. Thank you.
There's lots of interesting things happening at the moment, partly because of pulsars. People now watch the stars and watch for things that change in brightness. It's partly because we have better equipment. In the old days, you had to look and look and look and look, take a very long exposure to see it. But now with this, what we call time domain, we are seeing many exciting variable things. So, for example, the pulsar astronomers, they're studying pulsars, and from there, suddenly, there is one very strong pulse. And when they estimate the distance, it's not in our galaxy, it's away, away beyond our galaxy. It looks like one pulse from a pulsar, but it must be much bigger. We call these things fast radio bursts, and the Canadians have just published a catalogue that I think has about 3,000. Most of them are single, a burst, a burst, a burst. But some repeat, burst, burst, burst. It's gone quiet, burst. So a few repeat. So we know them as fast radio bursts, and it's a big mystery what they are. We can position some of them. They come from big galaxies, but not the center of the galaxy, somewhere outside the center, an ordinary address in the galaxy. What they are, don't know, wait and see, maybe.
There's another possible answer to that question. The mission I'm working on, called Plateau. The idea is to look for planets like the Earth around stars like the Sun. At the moment, we haven't found one. People have found thousands and thousands and thousands of planets. There's more than 4,000 confirmed planets at the moment. But every time you hear, this is a new Earth, think that it's been written by the New York Times and edited by Donald Trump. They aren't. The Plato mission, what it's going to try and do is look for the very, very rare cases where you've got a star like the Sun out there and a planet like the Earth just passes in front of it and hides maybe a 10,000th or 100,000th of the light of the star and produces a little tiny dip in brightness that lasts for an hour, 2 hours, maybe 5 hours, and then the star continues absolutely normal for another year. So we think that these planets are out there somewhere. It's ridiculous to think that our Earth is unique. Every time we thought our Earth or our Sun is unique, we've been proved wrong. The Earth isn't the center of the solar system. It isn't the center of the universe. Not even the Sun is the center of the universe. Our galaxy is a little galaxy. Every time we've thought that we were special, we were wrong. So there must be planets like the Earth out there somewhere. We'd love to find them. It's going to be very, very difficult. The mission will launch in December 2026. Hopefully, please, if everything works, if nothing breaks, we'll be staring at the sky for 8 years, and we hope we will discover 1 or 2 of these planets. If that happens, that will be utterly amazing. I think it will transform our view of the universe.
Do you know they are now finding planets that have no star, no sun?
Oh, yes.
Sometimes they're called rogue planets,
Yeah,
which I think is unfair.
There's always a troublemaker out there somewhere, yes. But we want, it's very specific, star that looks like the Sun, planet that's more or less the size and distance of the Earth. Those are the ones we're interested in. But we'll accept any planets, rogue planets, whatever. We're not proud.
Hello, it's wonderful that you're here. It was a wonderful talk. I just wanted to that, you know, I'm a teacher, and every year we do like a special project about women in science, and every year they choose to study you. There's at least one group who chooses to study you. So what can I tell the kids when this year they study you again and they choose to learn about you? What can I tell them, especially the little girls that are going to be learning about you and what you did?
I was lucky in that my parents encouraged me to do science, helped me get to do science, because in my school in Ireland, girls did not do science. Girls did cookery and needlework. The boys did science. But my parents helped me to do science. And it turned out I was good at it, especially good at physics. Now, if I had not had my parents to telephone the school and say, Jocelyn will do science, full stop. If I had not had parents like that, I would not be here. So if girls think they might be interested, they should be encouraged and allowed to. But I don't know how it is here, but in Britain, if you look at advertisements for toys, for boys and for girls, the girls' toys are tea sets, princess kits, makeup kits. The boys' toys are exploring, adventurous. And already very early in life, girls are encouraged to be little princesses, pink princesses, and boys are the big organizers, leaders, commanders. And somehow we have to change that because we are wasting so much girls' brains. So please encourage any girl who wants to do science. Tell her, of course she can do science. And she could have a good life doing science. Thank you.
Yeah, Professor Bell, first, thank you very much for being here today. It's a pleasure to have you here. And of course, congratulations for your seminal work and the nice discoveries you have been making for the last decades. So, also in relation with the movie we were able to watch at the beginning of this session, I would like to know your opinion about, let's say, not being alone in the universe, about the possibility of finding life, either microbial life, or perhaps, let's say, real little green men, you know? So intelligent life. What's your personal opinion on that?
The universe is very, very, very big. And even if the chances of there being life are small, there probably are other places where there is some sort of life. Whether it is intelligent life, I don't know. Whether it is little green men or people like us, I don't know. But the universe is so big, I think there must be elsewhere. Whether we can communicate with them, that is perhaps less likely. But in terms of existence, I think there must be.
Comes back to what I said earlier. Every time we thought we were special, we were wrong. We don't even know if we're the only life in our solar system. People are still arguing as to whether or not there is life on Mars. There are tantalizing hints that maybe Mars has or had life. We don't know. People are looking at the satellites of Jupiter, Saturn, thinking it's possible. If we don't even know if we're alone in our own solar system, in a galaxy of 100,000 million stars, in a universe where there are 100,000 million galaxies, are we so special that we're unique? We're the only life in the universe? Not necessarily intelligent life, but at least the only life in the universe is on our planet.
Indeed. Universe is very big.
Hello here. Well, thank you very much for your presence. I think it's a very an amazing talk. And I just want to ask you about the imprecision of masses measured in Betelgeuse, and also the size and the distance. I was surprised about that, and I would like to know how could we do better technically, or what we need technically to better measure that imprecision.
Mm-hmm. Right, okay. Jan Uwe, cover your ears up for a few seconds. It turns out that at ESA, we have a very special mission called Gaia. It's been mentioned. Measures the positions and brightnesses of stars with incredible precision. It can measure stars out to tens of thousands of light years distance with considerable precision, better than anything that exists. What's the problem? Betelgeuse is too bright to be measured with this super sensitive satellite that is intended to measure stars of magnitude 18, 19, 20, 21. Betelgeuse is around magnitude 0. This is very unfair. Now, it turns out, because I have been asking about this and annoying people a little bit, this is where you need to close your ears, because if they find out I'm causing trouble again. They did measure Betelgeuse with Gaia, but they used a very special technique because it's so bright. And it turns out that these measurements will be extremely difficult to analyze. Now, I don't know if Jocelyn's free for 6 months or so sometime. They're looking for a student with a lot of patience who could sit down with these measurements, spend about 6 months and try and make some sense of them. With all the problems of COVID and the catalogue of 2 billion stars that the satellite is producing, they just haven't had time to worry about one star, Betelgeuse. But I am going to keep molesting them until finally they do something about it. One day, hopefully in the next 4 or 5 years, we'll have the answer. And we'll know exactly how far Betelgeuse is, and we'll have a very good idea of exactly how massive it is. But unfortunately, it won't be tomorrow. It's going to be a project for somebody very dedicated to look at these special data.
Hi. Here. Hi. I'm an engineering student, and it was resonating a lot with me what you said when you arrived at Cambridge and how you felt. Does the imposter syndrome ever go away? Like, you've been told your whole life by different people that you shouldn't be doing science, even if your parents are constantly, they're a force behind you, and you eventually reach the point where you are studying what you like. Does the imposter syndrome ever go away? Do you ever feel like you are one amongst the rest of the professionals in the field? And my next question, Mark, you mentioned that we don't know basically anything about dark matter. Is there any relation between dark matter and the stars that we are seeing today? Thank you.
Just 2 easy questions.
Yeah. Do you want to go first?
After you, ladies first.
So, imposter syndrome gets less of a burden. It takes a long time for it really to go. I'm still conscious that I'm often one of few women in a male environment. But at the same time, the male environment has become more aware of women and how they are feeling in that environment. So it gets better. It's pretty well gone, I'd say, but it does take time.
Have you ever thought of working for ESA? Come to ESAC. Some of our most brilliant engineers and scientists are women. They're just normal scientists and engineers and we depend on them. I don't say it's a perfect environment, but it's a pretty good place to work. Think about it. Seriously, a lot of our most brilliant engineers are definitely women. And I don't think of them as women, they're just colleagues. It's the way it should be, isn't it, Jocelyn?
Yeah.
The question about dark matter, I wish you'd ask a difficult question, you know. We don't know what dark matter is. There are plenty of ideas, there are plenty of theories. Some of them are crazy, but as I think it was Richard Feynman said, your idea's crazy, but is it crazy enough to be true? People have thought dark matter could be black holes, could be neutrinos, could be... The real answer is we have no idea. But for every atom that we see out there in space, there are something like 15 atoms, they're probably not atoms, that we can't see, and of a nature that at the moment we can imagine, but we can't say for sure what it is. It's there. What it is a mystery. Now, this actually is more probably Jan Uwe's subject than mine. So I'm going to get Jan Uwe into trouble, but he probably hasn't got a microphone.
Right.
Well, I can really only reflect, by the way. Am I in the camera?
Come on.
I don't want
Camera's
to
over there, Jan Uwe.
Yes,
no,
okay.
If you face that way.
Yeah, okay. That's good? Is that good? Yes, all right. Okay.
Look into the camera.
Introducing myself, my name is Jan Uwe Ness. I'm the chair of the ESAC faculty. And yes, dark matter is a mystery. I mean, you've already said it. It can be anything. There's also a theory that dark matter may actually not be matter. It may be different physics. You know, how do we know that the gravitational constant is constant? Maybe it varies. So maybe just the laws of physics are different. I'm not saying that it's true. We're not the New York Times. But it is a theory that has been debated quite hotly in the community. It's probably wrong. There have been evidence, people studying the spiral arms of the Milky Way, and they noticed that not only matter interacts with dark matter, but dark matter also interacts with matter. And that means it's got to be something, it's not laws of physics bearing. Yeah. If that helps you a little bit. Not a specialist in that, but a good friend of mine is, yeah.
There's a lovely PhD project there for somebody, if you're interested.
Yeah. Yeah, if you need PhD projects, there's tons of ideas. We have more ideas than we have, how should I say, manpower? Is that allowed?
Persons.
Person power?
More ideas than there are sane.
Let me say resources.
Yeah.
Human resources.
Well, the last question, and before that, I must say that in a couple of weeks or 3 weeks, I don't remember exactly, Professor Juan García Bellido, who is here right now, is going to tell you about the connection between dark matter and black holes, primordial black holes, if they exist, or have existed. Okay, he's going to talk about that, so don't miss that. So the last question.
Well, hi, it's a pleasure to meet you here. And I have a question related to the paper in Women in Science. And my question is, well, I'm a second-year PhD student, and what advice would you give to younger PhD students as me, women? Thank you very much.
Believe in your own work. If you think your work is good, it's good. You hold on to it. It's true. You keep saying it's true, it's right.
Thank you very much, Dr. Bell, Dr. Kidger. Give an applause to them, please.
Thank you.
Now must go on. Thank you very much. There are still some things remaining. So let me introduce Dr. Jan-Uwe Ness. He's a German astronomer working at SAC and the European Space Agency Center, which is very near Madrid. The astronomy center of the European Space Agency is 20 kilometers away from Madrid, about. So he's going to talk something about the station, and welcome, and thank you very much for coming.
Thank you very much for hosting. Let me start telling you a small secret about myself. I also suffered imposter syndrome when I started. I'm a man, so it's not a female thing. Yes, okay. So as I already said, I'm the chair of the faculty. This is a collection of scientists, about 150 scientists at the European Space Astronomy Center, ESAC. How can I swap the slide, by the way? You got it. Oh, yeah. Mark, yeah. Thank you very much. Okay, let me guess which button it is. Oh, I screwed it up. Wrong way around. Okay, so we are a site that it's a bit outside of Madrid. You see on this wonderful picture, we have a combination of buildings and satellite dishes. These are not receiving satellite television, but these are communication dishes with which we tell the satellites what they need to do. We call that uplink, and we receive the data that the satellite are doing. And here's one of them, diameter of 15 meters, together with a model of the Herschel satellite. Mark Kidger has worked for several years with this mission, which is an infrared mission. We also have here a picture of a medieval castle that is just next to our site from the 15th century. And we kind of have old and new in front. It's a little bit younger. It's the ISO satellite, again, an infrared satellite. And you see there's crowds of people. In 2018, we had an open day where we had about 5,000 visitors. And like here in the planetarium, within an hour, all the tickets, 5,000, were gone. So it's a very popular site. ESA is doing research with many, many missions, past, present, future. So here in this graph, you see the cosmic observatories. I think is there a laser pointer here? Yes, there is. So you see the Herschel and the ISO right next to each other, which I've just shown you the models. And you see here the electromagnetic spectrum. That's something Jocelyn always likes to start her science presentations with, show the electromagnetic spectrum, where you have the, all the, microwave, submillimeter, infrared, optical, ultraviolet, X-rays, gamma rays, okay, and gravitational waves. And you see we have missions in everything. We also go to the planets, visit the planets. We have, our Earth here. We have Cluster. We have our Moon. Comet Interceptor. We have Mars with Jupiter. We study the moons of Jupiter with JUICE, having gone to Saturn, and so on. There is a whole bunch of missions also to the Sun that we operate. I can't name all of them. It's a huge number of missions we're operating. Now, ESA is the European Space Agency is distributed over several sites worldwide, but of course with a focus on Europe. So we have, Brussels, we have a headquarters in Paris, we have Pfaffenhofen, we have ESOC, Darmstadt, that's from where the missions are operated. ESTEC, that's where they're developed. And we have ESAC in Madrid, where the science operations is taking place. So essentially, our strongest partner is ESOC and Darmstadt. They operate the telescopes, and we tell them what the telescopes should do in space. ESAC itself, as already mentioned, is a bit away from Madrid. So you have here the center of Madrid. You have here Pozuelo de Alarcón. Majadahonda, and then when you go out here, it's between these two rivers, the Guadamonte, we have Villafranca de Castillo, Villanueva de Cañada, and that's about the area where it is located. Okay, tomorrow we'll host Jocelyn Bell in our institute. She will give a presentation on women in astronomy. And I encourage you, I don't know whether the slides will be available to the participants online, or you just take a quick picture. This is the YouTube link where you can follow her presentation live. It's also going to be recorded and going to be available after the presentation. Here are this longer link are other presentations that we have archived. Thank you very much.
Thank you, Jan-Uwe. Well, we are getting to the end, so we have two more things for Dr. Bell. We have a nice present. I forgot to tell you that we belong to the City Council of Madrid, and we are hosted also by the La Caixa, Fundación La Caixa, we have the honor to be with them also to prepare very activities and so on. But we have a presentation, we have a gift for you, a present, no presentation, a present for you. not presentation, please. Thank you very much. Give me, please.
Thank you very much.
This is for you. Thank you very much.
Thank
Welcome
you very
to Madrid.
much indeed. Wonderful. Thank you. It's been wonderful to be here. So thank you, sir.
I will show you, as it has been written by the director of the Imprenta Municipal de Madrid. And this is a book, well, opened later because
Yes.
it's so nice, the envelope.
Thank you very much.
Thank you very much.
Thank you. They're very kind of you.
Okay, thank you, Dr. Bell. And now we are almost finishing. Now we are cutting the presentation in the YouTube because now we have a second gift for you, Dr. Bell, which I will tell you a joke.